Howdy everyone, welcome to our Chapter 11 example problems. In these videos, we'll have one for each chapter. I'm going to go over some of the more common or important types of problems from each chapter, or some of the ones where students tend to have a little bit of trouble with the procedure of how do you set up a problem, how do you work through it, what are the key steps to identify. So while this won't cover every single problem type that you'll see in a homework set or on a test, I am hoping that it will help you with the key ones that will get you started, help you understand the material better, and not just be stuck not knowing what to do. So in Chapter 11 here, we're talking intermolecular forces, and the first thing that we want to do is always be able to identify them. Because if we can identify intermolecular forces, then all the other questions about surface tension, viscosity, melting point, boiling point, all those things are going to come from the intermolecular forces. So if you can solve this first part, then you'll be able to get the rest of it just from that. So for this first one, we're going to do 11.19, all three parts, and we want to identify the intermolecular forces. The first thing is that everything always, let me get my pen up, is that all things have dispersion forces. Right? That's automatic. At no time, there's nothing that does not have dispersion forces. They might be weaker, they might be stronger, but everything at least has that. So we can always put that down first. The next thing we're looking for is going to be the possibility of dipole-dipole interactions. So for that, we want to be able to say, well, is there a chance that the molecule is polar? So we can use the same approximation we used in Chem 105, where we said if you see fluorine, oxygen, nitrogen, or chlorine, then go ahead and assume yes, that it's a polar bond. And then we got to use our stuff from Chapter 9 of, well, let's draw the molecule out. Let's see what the three-dimensional shape would be. Is it a polar molecule? So we'll look here at this first one, SO2, sulfur dioxide. It has oxygen, so there's a chance it might be a polar molecule. That means we've got to draw the Lewis structure and see what shape is it. So we'd put sulfur in the middle. We'd have oxygens. Give them the octet. When we count up, we've drawn 16 electrons. When we add up the valence electrons from these three, we're supposed to have 18 total. So that means 2 are missing. We put them on the sulfur. We now look and say, oh, the sulfur is missing 2. It's only got 6 electrons. It needs 8. So we'll take these 2, erase them, move them to make a double bond. And there's our final picture. And now we say, okay, from Chapter 9, there are 3 domains around the sulfur. That's trigonal planar. Oh, but only 2 of them are bonding, these 2. That's a bent molecular shape. With polar bonds and a bent shape, this is going to be a polar molecule. So now when we go through, we say, okay, SO2, it's going to have dispersion forces. It's also going to have dipole-dipole. It's not going to have hydrogen bonding because, well, there's no hydrogen. Remember, for that, we need to see hydrogen attached to either fluorine, oxygen, or nitrogen. So we don't have it here. So this one's got dispersion, dipole-dipole. That's it. Now we look at part B. And we say, okay, there are some O's, there's an H, but this COOH, that's a very special arrangement of atoms. That is a way that chemists indicate that it's a carboxylic acid, which is an organic functional group. It's an arrangement of atoms. Whenever you see COOH, it means this, that there's a C double bond O to another O to an H. That's the acid. And then there's a 4th bond on this first carbon, and it's whatever else is in that molecule. So in this case, it's just a CH3. Now here we don't have to worry about the overall shape too much because when we see acid, we know that, yes, that's going to be polar. So when we say, okay, it's going to have dispersion. It's going to have dipole-dipole because of the O's. And then we say, oh, look, there is a hydrogen attached to an oxygen. That means we have a hydrogen bond donor, that's the H. We have a hydrogen bond acceptor, that's the O's. If it has both, it will have hydrogen bonding. Okay. For the third one here, it's got dispersion, because everything does. But we don't see FO, N, or Cl, so there's not going to be dipole-dipole. And that H is not attached to FO or N because they're not there, so it's not hydrogen bonding. It's just dispersion. So sometimes it is just that easy to say, hey, it's dispersion and nothing else. Sometimes you got to draw a Lewis structure. Sometimes you got to know what the shorthand means. But this is why we're doing this practice. Say, okay, where can we get this stuff from? All right. The next section that becomes important is about vapor pressures. It is a key thing, and we use this in the research laboratory, that sometimes we have solvents that we want to evaporate to remove them, because that's the easiest way to maybe separate chemicals, is we want the solute that's dissolved, we want to pull away the solvent, but maybe the solvent has a really high boiling point, and that could decompose the solute. We don't want to, or it's not safe to go that high. We use solvents sometimes that don't boil to 200 plus degrees Celsius. But if we pull a vacuum on them, if we lower the pressure, then you see, oh, boiling points get lower and lower as we lower the vapor pressure. So here's a diagram that has a few molecules on it, and we want to be able to read this to say, well, what changes would occur or what changes would need to occur. So here it says, what would the boiling point of ethanol be at 200 torr? All right, so here's 200 torr. We just are going to follow that to the left until we find the ethanol curve, which is here, the orange one. So it's right about there on the graph. And I'd say, okay, that midpoint's going to be 50. So I'm going to say that's about 47 degrees Celsius, roughly. It said, what pressure would it be when ethanol boils at 60? Okay, well then we find 60. We go up to our ethanol line. That's about here. All right, that's more than halfway. That would be above 300, maybe about 320 torr. Right. Let's see, the boiling point of diethyl ether at 400 torr, so that's the red one. Come to 400, we go across, we find it, and we say, okay, that's under 20, maybe that's about 17 Celsius. That's less than room temperature, so it's actually a very tricky thing. If you ever pull a vacuum on diethyl ether, it will probably start boiling on its own, because normally here it boils at 34. That's less than your body temperature. If you hold it in your hands really good, it'll start to evaporate really quickly. And then what's the pressure when the ether boils at 40? Well, there's 40. We follow it all the way up, and it looks like, hey, that's right here at the top. Well, 2, 4, 6, 8. That looks like about 1,000 torr at the maximum of the chart there. But if you ever have questions about vapor pressures, that's all you have to do. Either take the pressure they give you and find the temperature, or take the temperature they give you and find the pressure. But it's just reading a graph. It's a skill that we're hoping that you've developed already, but if not, that's how we use it on these. All right, for our final one, using phase diagrams, we want to say what are the phase changes that might happen. We're doing 11.61b. I skipped A because it had you start like right here and go up to 20, and with this graph, this is not from the book, but the book one's not any more helpful. It is really hard to see, do you cross this line or not, to find out does it melt. So we're just going to do part B where it's definitely clear. It says we start at 100 Celsius and 0.5 atm. So here's 0 atm, so 0.5 is right about here. We go over to 100, so right about there is where we'll start. It says we're going to cool it down at constant pressure, so we'll stay same pressure, so let's go straight across to the left, all the way to -10, which will be, well, somewhere over here to the left of 0. So we'll just put a dot there. And they want us to know, want us to list what phase changes happen. And so here you just have to look and say, well, if I start as a gas and I cross this line into liquid, well, number one, it's going to condense. Right? When a gas turns into a liquid, that's condensation. If you go opposite liquid to gas, that's evaporation. All right, but then we keep going. It looks like, hey, we cross from liquid, we cross the other line into solid. And so that phase change we can either call freezing or we can call it fusion, because that's the taking the liquid and fusing it, making it combine into a solid. So in this case, even though it's one temperature change, we have two phase changes. So always watch out for that. There might be more than one answer that happens. If we were doing a vertical one, if it said, oh, the temperature maybe starts here at 50 Celsius, and then you go up to, say, 50 ATM, so up to about here, we'd say, okay, yeah, we go up there, and oh, yeah, we start at gas, we cross the line to liquid. Well, there we are. We're at, or if we start here, some low pressure, then yeah, we will again condense from a gas to a liquid. All right. Remember, if you go above the critical point, then you just have supercritical fluid. As long as both temperature and pressure are above those numbers, then it's supercritical. And the triple point is when all three phases are present. They're in equilibrium. It's a really weird thing, but it happens. All right, so I hope this was helpful for Chapter 11. Again, I would focus a lot on your intermolecular forces because so much stuff is based off of them. Once you know what they are, you can answer all the other questions. But be familiar with the graphs for phase changes and vapor pressures because that's a very common thing of, here's a picture, tell us about the picture. Make sure you understand how they work. All right, thank you very much. Have a good day. I'll see you back for Chapter 12.